Good day, everyone, and welcome to this Lightbend webinar for May 23rd, 2019, titled Running Kafka on Kubernetes with Strimzi for Real-Time Streaming Applications. My name is Oliver White, Chief Story and MC at Lightbend, and joining me today is my colleague Sean Glover, who's an O'Reilly author, conference speaker, principal engineer at Lightbend, and the creator of the recently released Kafka Lag Exporter OSS project. While I introduce today's session and let everyone get their popcorn out, I would like to ask our audience a quick poll question. Where do you run Kafka in production for your most important project? If you're joining us today, then you're probably using Kafka, most likely on statically defined clusters with everything running as close to the metal as possible. But with the explosion of Kubernetes and other container orchestration tools, running Kafka on container orchestrated clusters is now becoming more demanded. And when it comes to Kubernetes, the best way to run stateful services on it that have complex operational needs is to use the operator pattern. So that means more new stuff to learn, right? Well, this is where we meet Strimzi, which is the leading open source project to run Apache Kafka and ZooKeeper on Kubernetes. As an engineer on the Lightbend Pipelines team, Sean has spent a lot of time working with tools like Kafka, Kubernetes, Spark, Akka streams, and so on with Lightbend Platform. So he knows how manually intensive and tricky it can be to get everything right. And that's why it's great to have him with us today to walk us through how the Strimzi Kafka Operator works to make many operational tasks in Kafka a lot easier, such as the initial deployment and updates of a Kafka and ZooKeeper cluster. Specifically, we'll spend a little time looking at why the operator pattern is the best way to run stateful services with complex operational needs like Kafka, how to manage Kafka resources like brokers, ZooKeeper, topics, users, and mirror maker configurations using Kubernetes custom resources, and how to use transient and persistent volume storage options, and how to make operational tasks easier, such as rolling cluster updates and upgrades, scaling brokers, moving brokers, monitoring, and running multiple Kafka clusters on the same Kubernetes cluster. Well, thanks to everyone who replied to our poll. Now, just for a little bit of housekeeping. As always, today's webinar is made possible only by people like you encouraging your company to become one of Lightbend's hundreds of happy customers, like our client MoviePass, which if you don't know much about them, they are kind of like a Netflix for movie theaters. They're looking for a talented Scala Akka Play engineer to join their main platform team in New York. So if you're in that area, you can check out more about this position and other open positions with Lightbend customers on lightbend.com under the About tab. Many of you ask, and yes, the answer is we will be recording this webinar and it will be shared with you in the next week or so. If you have questions, you can add them to the GoToWebinar control panel and we'll see if we can get around to them in the Q&A part of today's session. And of course, if you are an existing Lightbend customer, then you know that you have unlimited access to our expert engineering teams through the customer portal. So you can go there and ask any additional tech questions, what ifs, how-tos, and best practices for any of the tools that we present today. Okay, that's all from me. Let's hand it over to Sean Glover. Sean, thanks for joining us today.
Thanks. You can hear me okay?
Yeah, it's sounding good.
All right. All right, well, thank you for joining everybody. Today we'll be running a webinar called Running Kafka on Kubernetes with Strimzi for real-time streaming applications. And I've delivered this presentation in a few different forums in the past, where it was called Kafka in Jail with Strimzi. And then last year, I think we delivered the same or similar webinar, but focused on DCOS Kafka, which is similar to Strimzi. Anyways, let's get started. So I'm a principal engineer at Lightbend. I'm currently a member of the Lightbend Pipelines team. So this is a commercial software product from Lightbend. And at the end of this presentation, I'll quickly show an overview of that. But for the last couple of years, I've been working on a product called Fast Data Platform, which is now known as Lightbend Platform. And among supporting our core open source stuff like Akka and Play and Lagom applications, we also provide expertise and support for data streaming technologies and stream processors specifically, like Spark and Akka streams, Kafka streams, and Flink. as well as the infrastructure to run everything on, so Kubernetes and Kafka. And I've been specializing in the Kafka ecosystem. So as a result, I've contributed to Kafka itself. So the Kafka streams for Scala DSL was a contribution I worked on with a colleague of mine, Debasis Ghosh. The transactional support in Apache Kafka, which is our Akka streams to Kafka connector. Strimzi, of course, and Kafka Lag Exporter, which I recently open sourced, and I have a slide for at the end of this presentation to quickly showcase. And then DCOS Commons SDK is a way to run stateful services on DCOS and Apache Mesos, which is what we were using as our infrastructure base before we moved to Kubernetes. So we made some contributions there too. So let's get started. Operations is a difficult thing to do right. We often hear this statement that technology will make our lives easier, and that's certainly the case. But the more technology we have in our lives, the more difficult some things become, like operating that technology. And that's certainly the case for Kafka, which has a profusion of endpoint configuration and various things that, as an operations engineer, you need to be familiar with in order to run it well. So Strimzi is software that helps running Kafka easier, make running Kafka easier on Kubernetes. And it automates a lot of the common operational tasks that you need to do on Kafka to run it well. So let's talk about a motivating example first. So this is some reasoning as to why something like Strimzi or software to help operate a Kafka would be useful. And I chose the zero downtime Kafka upgrade because this is a fairly complicated thing to do without introducing any errors in the process. So upgrading Kafka with zero downtime has these 5 kind of high-level steps. The first is that we want to pin the actual version of the protocol that brokers use to talk to one another, the inter-broker protocol version. And this is important because when we do the upgrade, we don't want new brokers speaking a new language and the old brokers speaking an older language, and they can no longer communicate. Obviously, that would be bad, and we'd have some kind of split cluster situation that might arise. So this configuration isn't set by default, and it will use the newest version by default. So it's important to set this to the current version of your Kafka cluster before you run an upgrade, so that the new brokers that come online can still speak the old language while the upgrade's happening. And then log message format version is similar. That it's the version of the messages that the schema for the messages that are produced by Kafka clients and consumed by Kafka clients. If you want to use new features of Kafka, then it's important to stay on a more recent version of the log message format version. But we want to make sure that we have an expected version for this as well, so we don't break any of our clients when we do this update. Next, we download the new Kafka distribution. We perform a rolling upgrade. So this is similar to the rolling update we did in the first step. Go to one broker at a time, upgrade its distribution, bring it back online. Then once all the brokers are upgraded, we can actually upgrade to the latest inter-broker protocol version because they can now all speak that new language. And then optionally, we can upgrade our clients or ask our users to upgrade the clients and eventually update this log message format version. This isn't absolutely required because clients and brokers are fairly resilient with negotiating a protocol that works. They're both forwards and backwards compatible. And if you're using fairly stable Kafka features, then you likely have nothing to worry about there. But nonetheless, it's useful to use the latest version so that you can take advantage of the latest efficiencies and new features of the Kafka clients and brokers. So in this example, we had 3 rolling updates. These were like configuration updates for those various broker properties, as well as 1 rolling upgrade. And each one of the steps in all of these rolling updates and upgrades requires us to securely log in, do some kind of configuration linting to make sure the broker can accept the configuration that's applied to it. We have to do a graceful shutdown, and this is really important because we want to make sure that clients will, if they're connected to our broker or if other brokers are connected to it, that they gracefully switch to another broker. So we do things like move active partitions off of the broker we're bringing down, and we signal to the broker, the other brokers that we're going down and not to like synchronize with us until we come back online. So that's really important. Then on the flip side, we need to bring the broker back online, and it's important to wait for the broker to signal that it's in a healthy state before we move on in our rolling update. Because if we don't wait and there is some problem with applying a change or an update to a broker, you can imagine that we just replicate that same problem across every broker, and soon your whole cluster will be down. So this operation has a lot of moving parts. It's error prone to do manually, and it's difficult to model declaratively in tools like Ansible and Terraform. So this is where software can help us out a lot. So in the software world, there is a concept known as continuous delivery, and Jez Humble wrote a book all about continuous delivery, and it's basically about automating our deployment of our software from all the way from pushing a commit to deploying it to production. And this requires a lot of discipline. It requires a lot of work to automate all these pieces, but it has a lot of advantages. And this deploying to production is usually known as the last mile in software development. It's usually kind of taken for granted as, yeah, we'll get around to doing that. There's a lot of things that can go wrong when you're doing it, obviously, because you're messing with a production environment. And because of that, it becomes a painful thing to do. And some software organizations will avoid to deploy to production as much as possible because they don't want to upset things. So Jez is saying in this book, if it hurts, then we should try and automate it and make it easier. So if it hurts, do it more frequently, meaning automate it so you can do it more frequently and bring that pain forward, automate that pain away. So I think the same applies to infrastructure that our software depends on, and if you're building a data platform, Kafka is an essential part of it. So some of the things we can automate, and that Strimzi helps us with, are initial deployment of Kafka itself, the deployment of ZooKeeper that goes, because that's a requirement of running any Kafka cluster, it also manages a ZooKeeper cluster for us. Doing things like replacing brokers. So if we have a large cluster, odds are we'll have to replace brokers fairly frequently. Reallocating partitions across our brokers in order to fully utilize everything efficiently, and then scaling brokers, so decommissioning them or adding them, it can also help us with. So let's talk a bit about cluster resource managers first. So there's two main generalized cluster resource managers, and when I say generalized, I mean they can run any kind of workload that you wish to run. There's lots of specialized cluster resource managers out there too, but these allow us to kind of run anything we like. And cluster resource managers are similar to an operating system, where an operating system abstracts away the hardware on your computer. A cluster resource manager abstracts away those resources across a whole cluster of computers. So Mesos was one of the first of its kind to be open sourced way back in 2009. And it was really good for running, kind of stateless workloads efficiently. And then later came DCOS, which brought together a bunch of projects that kind of sit on top of Mesos and make it easier to run stateful workloads like databases like Kafka. And it does its job fairly well. But the problem with DCOS, in my opinion, is that it brings together a whole ecosystem of projects that collectively can get something done, but all have varying degrees of quality in terms of documentation, in terms of their implementation, bug fixes, and so on. There's a lot more to learn in order to kind of run your whole infrastructure on Mesos. Whereas Kubernetes, open sourced or created by Google and inspired by their internal cluster resource management tool, org, had the benefit of learning from internal mistakes and experience at Google, as well as Mesos and how things run on Mesos. And they're able to internalize a lot of these features into the core of Kubernetes and make it easier to get started with running just about any kind of workload. And in my opinion, it's a lot easier to get started with Kubernetes, and you have a better consistency in terms of quality of the software itself and documentation and things like that. So cluster resource managers rely on containers in order to provide task isolation, as well as to do bin packing, which is basically how they slice and dice resources to be allocated across your cluster. So when we talk about containers, we're talking about Linux containers in this case, which are basically two features of the Linux kernel. So C groups are used to constrain resources like CPU and memory, and namespaces are used to isolate the file system itself, as well as process trees that run on executables and other files we have in that file system. So Docker is just it's a project that uses containers to run, but it's basically a way to describe and share our containers in an efficient manner. There's other solutions out there too, like RKT, and then Mesos runs its own containerizer too, but Docker is obviously the favored and most popular right now, and Kubernetes accepts it kind of as the default option for our containers. There's also container-like things on other operating systems. So FreeBSD has a feature known as jails, which is very similar. And then Windows has containers now too, which I don't know a lot about, but I assume work in a similar way. So I'm going to talk about Kubernetes, but just the bits that are important for you to understand in order to know how Strimzi works and how stateful workloads run on Kubernetes. So the first thing to talk about is the operator pattern. So this is a really important software architecture pattern that's actually used internally in the implementation of Kubernetes itself. So it's made up of two main things. You have a controller/operator. People kind of call them these things interchangeably. And it's a piece of software. It could be a Java application, it could be Go, it could be anything really that can interoperate with Kubernetes APIs. Strimzi is written in Java, and there's actually several operators within Strimzi, but the main operator called the cluster operator has this implementation, like all operators do. It's basically a infinite loop, and it's called the active reconciliation loop. And basically, it listens for changes to some kind of configuration, and that's the other part of the operator pattern, the configuration. And when the configuration changes, it will get that new configuration, which is known as a desired configuration, and compare it to what is currently applied to the thing that we're operating, so Kafka in this case. And it's going to build an automatic reconciliation plan for us. And this plan is basically a set of operational steps that are required in order to bring the desired state into reality, to make it the current state. So in Kubernetes, that configuration state is represented as custom resources. So in Kubernetes, you have resources like pods and replica sets and stateful sets, services. These are core resources of Kubernetes, but you can extend Kubernetes by implementing your own resources, and these are known as custom resource definitions. So Strimzi creates a couple of these. The main one is the Kafka custom resource, and this has all the configuration we need to actually run the cluster. And this is what we initially deploy and update in order to manage our cluster. It's sort of our interface for managing our cluster. Running stateful services in Kubernetes is is difficult, but there is there are some core things that make it easier. So stateful set is the core resource we need to be aware about. And this is basically a container around a group of pods, stateful pods. So stateful sets are generally used to run things like databases, such as Kafka or Cassandra or HDFS or anything like that. And these things typically require some sort of stability. They have a bunch of requirements. So they need to be stable to a machine. They can't be moving around too much, or preferably not at all while they're running. And they have a stable network identity. So they have a stable host name, they have a stable IP, and they have stable storage, most importantly. So storage for the pod that can live longer than the lifetime of the runtime of that pod. So if the pod goes down for whatever reason, we can be assured that when it comes back online, it can be reassociated with its state, its storage, and continue along. So that's important. It also facilitates things like ordered deployments and configuration updates on our behalf. It makes it easier to do graceful deletions and terminations of pods within the set. And it provides sort of a naive way of doing rolling updates, where it just kind of does rolling updates one at a time. But with an operator, you can control how this update happens. You can either run the naive implementation, which is one at a time, or come up with your own strategy to do updates based on whatever is suitable for the thing you're operating. So on the right-hand side here, we have a simple stateful set. This is a Kafka Brokers stateful set. It can have as many pods as you like. So in this case, we just have the one, and they're basically just the name of the pod spec you define in stateful set, and then an iterating number, incrementing number, integer. So they start from 0. And if you don't create storage for this stateful set beforehand, it will automatically create it on your behalf, assuming you have dynamic provisioning enabled in your Kubernetes cluster. So it'll create what's called a persistent volume claim, which will eventually get bound to persistent volume. So a little more detail on how that works. So a persistent volume claim is a way of abstracting away storage. So just like we abstract away CPU and memory, we don't really care which CPU or what memory or what server CPU and memory is on. Persistent volume claims allow us to do something similar for storage. So instead of just using local storage, which was pretty much the only way to do it before, we can just describe the kind of storage we want, and it will get automatically assigned to us. It could be local storage, or it could be some distributed block storage solution like cluster, or on the cloud, something like EBS, which is totally independent from the node or whatever node you happen to be running something on. And when it's abstracted away like that, we can easily follow, a pod with the storage can easily follow a pod. So say, for example, the kubelet, the underlying server running a kubelet dies and the pod goes down, but we have some distributed block storage. The storage isn't associated with that server, so it still exists. We can then replace that pod, run it on another kubelet, and remount that its EBS volume, its persistent volume, back. So that's a pretty powerful feature, and a good reason to use distributed block storage. So when we create these persistent volume claims, we're basically just describing what we want from a storage perspective. We just say, I want something this big, and I want this type of storage. You could have simple just EBS volumes, but all EBS volumes aren't created equal. There's different tiers of them that have higher IOPS capabilities or different types of hardware. So you might have different storage classes for each one of those. And then you can just say, I want that type of storage class. And when you create the claim, Kubernetes will look up your storage class, use the provisioner associated with that class to create it, in this case an EBS volume on AWS, and then mount that into the running pod. So Strimzi is an open source project. It's operator based. It was announced early last year, and it's had pretty much a full-time team of Red Hat engineers from their messaging and IoT department working on it since then. It's part of a commercial product at Red Hat known as Red Hat AMQ, which is a set of messaging technologies. So the streams component of that product is what Strimzi is Strimzi from an upstream perspective. But everything in this presentation is just talking about the open source Strimzi project, not the commercial bits itself. So the first operator to talk about is the cluster operator, and this is what is watching the Kafka configuration, the Kafka custom resource. And like I said earlier, the Kafka custom resource is what defines all the parameters we need to both configure and run the Kafka cluster that we want. So when we create these custom resources, and we'll see an example of that in a sec, the cluster operator will consume it, create a reconciliation plan, and create what we need. So when the first time it gets created, obviously it needs to deploy everything. So it'll create a stateful set, ZooKeeper stateful set. Those will have brokers and ZooKeeper nodes in them. And it's also creating another pod known as the entity operator pod. And this has two other operators that get deployed with every cluster. And this is to manage internal resources for that cluster, so the users and the topics associated with that cluster. We'll see an example of that in a second. But first, let's take a peek at how we define a resource. So this is a simple YAML resource for a Kafka cluster. It has a name, and this is the name that gets created on Kubernetes for the cluster. It has some configuration for the entity operator, which we'll talk about in a second. But most importantly, it has the Kafka and ZooKeeper configuration. So we have this is just broker configuration under the config stanza here. And listeners is just connection info, so what network interfaces to bind to, what ports to use. If you want to set up client TLS, we would set it up here. And then how many brokers we want. And then the resource allocation limits and requests for each broker pod. So in this case, we're just saying we want 3 gigs of memory. We don't have CPU limits or requests, but we can define those if we like. And then some storage parameters. So this is what eventually gets created as a persistent volume claim on our behalf. This is a storage class. This is our the size requirement we have, and we'll talk shortly about what this means, the type of storage for Strimzi. And then same thing for ZooKeeper here. Next, the entity operator is made up of 2 operators. So the topic operator is basically watching for Kafka topic custom resources. And then it'll create the requisite topic in Kafka itself when those get created in Kubernetes. And it also works the other way around. It has bidirectional synchronization. So if it sees a topic get created by some other means and shows up in ZooKeeper, it will create the resource in Kubernetes as well, which is pretty neat. And then there's the user operator, which is similar to how the topic operator works. You create a Kafka user custom resource, and this will automatically create secrets for you that you can provide to an end user to use to authenticate with your Kafka cluster. And you can also set up authorization rules for various Kafka objects, like topics, for that user. And then this synchronizes with Kafka too, but it only does it one way. If users get created by some other means, they don't get created automatically as custom resources like the topic operator does. So I'll show the topic resource. So here's an example. And you can see it's just a fairly simple YAML file. This is the name of the actual resource, but also the name the topic will have. It's important to associate it to a particular Kafka cluster that we have deployed. If you have more than one, especially, it's important. And then we set the standard config for the topic, so number of partitions, number of replicas it has, and then optionally we can define topic configuration overrides in this section here. And these are just from, you can find these in the Apache Kafka documentation. The storage modes supported by Strimzi are listed on this slide. So we have two main ones. The first is ephemeral mode, which is useful for just kind of playing around with Kafka. If we want to do some development or testing on our local machine or a dev cluster, then we might use this mode. And basically what it means is, we don't care about what the storage is for Kafka, just run Kafka. And in this case, it's creating what's called an empty dir volume. And this is just spun up automatically for us on the local node, usually, to the pod. And then it gets destroyed as soon as that pod goes down for whatever reason, whether we terminate it intentionally or otherwise. So because of that, it's not ideal for running a long-lived Kafka cluster because we want the storage to stick around in those failure cases or in those management cases where we change something. So persistent volume mode, or persistent mode, is using persistent volumes that we described before, and that's the ideal use case for most Kafka clusters, and certainly for production clusters. And then there's a third option, which takes advantage of a broker feature where we can have multiple disks associated with a single broker. And this is really useful if you want to increase disk throughput per broker or increase disk size, the total amount of disk available. So in this case, it just sets internally on our behalf this log dir's Apache broker config, which is basically a bunch of mount points to a bunch of persistent volumes. So let's go through some of the operational concerns and how Strimzi handles them on our behalf. So when we first install Strimzi, a lot of people get confused with this point that when we install the Strimzi initially, it doesn't create a Kafka cluster for us. It just installs the cluster operator and all of the supporting bits and pieces we need to create Kafka clusters in the future. So it just kind of enables our ability to create Kafka clusters. And then once that chart's deployed, we can then create Kafka resources like the one we saw before. So to install the open source chart, you just add the Strimzi repo, chart repo from the Strimzi website, and you can install the latest version like I have listed here. And of course, you can override the version you want to install and any values associated with it by just looking at the what values are available. I didn't realize before this presentation that I couldn't run on Linux. Otherwise, I had a demo prepared. Unfortunately, I can't show that to you right now, but basically I was going to apply that simple Strimzi Kafka resource I showed before and just show it kind of coming online. And we will probably provide some sort of secondary artifact as a blog post or a video, follow-up video, showing how easy that is. But you can imagine it's pretty easy if I was able to squeeze it into this presentation, at least the initial concept of that presentation. To connect clients to Strimzi, whenever we create a Kafka resource, a bunch of services get created on our behalf, including this bootstrap service, which is what is used to for clients to connect. So its convention is the Kafka resource name itself, followed by Kafka bootstrap, a load balanced name. So this is just a load balanced host name to all of the brokers on our cluster. And if you only have one Kafka cluster with this name, then that's all you need. But if you have some multi-tenancy set up in your Kubernetes cluster, maybe you have multiple namespaces where the same different Kafka clusters run, but they have the same name, then you'll need to fully qualify the service name, so it's not ambiguous when you try and connect to it. So that includes the namespace and this DNS suffix for Kubernetes services. And then of course the port. So if you're just using kind of unencrypted connections, you just use the default 9092 port. But if you have TLS set up, then you would use 9093. And I can't do the demo, like I said, but I can show you what I would have done. So I would have run this, I would have created the topic we saw before, and then run this deployment, basically. And it's just running the Kafka performance producer test against the topic that I created. And then this is the Strimzi service hostname that gets created on their behalf. And this thing would just kind of spit out some performance metrics based on the parameters we give it. Next, rolling configuration updates, probably one of the most common things to do as a ops person for a Kafka cluster. So this works like we described before. The cluster operator is watching for that Kafka resource to change. And once it does, it applies a new configuration to the stateful set. And then starting from pod 0, it deletes each pod and allows the stateful set to recreate it with that new configuration. So this type of rolling configuration update, I'm just referring to the, if I change the broker properties, this is what would happen. Other kinds of rolling updates would happen if you change other things in the Kafka resources, which we'll see on the next slide, but this is for configuration updates. So yeah, we delete the pod, it gets recreated, Kafka gets started, and then we wait for that readiness check to be good, and then we repeat this process for every pod within that stateful set. So in the demo, I was going to show how just adding a new configuration would trigger this rolling configuration update. We would have seen the one pod, the one broker that we have defined in the cluster go down, basically terminate, and then get recreated with the new configuration. Scaling brokers up is basically the same process from an end user perspective. We just have to edit the Kafka resource again, and we edit this particular property, the replicants property, and increase it to whatever our desired total number of brokers is. So in the demo, I was going to increase it from 1 to 3, and we would have seen that 2 additional pods would have gotten created in the Kafka stateful set and would have eventually come online. We'd have a 3-broker cluster at that point. And then whenever you're scaling with Kafka, you need to be aware of the partitions assigned, or you need to usually reassign partitions because Kafka won't do this on your behalf automatically. So if you want to take advantage of that new capacity in your cluster, you have to reassign partitions. So you can do that using various tools in the Kafka ecosystem, or you can use the bin script like I have highlighted here. And then finally, the back to the motivating example of actually upgrading Kafka clusters is a lot easier with Strimzi. So what we need to do in this case is, assuming we have a cluster already running of some older version, we just look at Strimzi. We go to Strimzi's webpage, find the latest version, and see what version of Kafka it supports. And then we, if one of the versions we want is in that list, then we update our Kafka custom resource, and we set the desired Kafka release version in that case, or for the desired release. And then what happens on our behalf, Strimzi is the cluster operator does this on our behalf, is it'll do the exact number of rolling updates it needs to in order to do a 0 downtime upgrade. So it's going to set the interbroker protocol version on our behalf, and it knows when it needs to do this because it knows when that version increments, and it's usually between like a major upgrade versus patch upgrades for Kafka. But nonetheless, it figures it out. If it needs to do that, then it'll do 2 rolling updates. If it doesn't, then it'll just do the 1 rolling update. And then optionally, we can update the log message format version. This is similar to how it was described earlier, Strimzi isn't aware of the clients connecting to Kafka. It has no control over those. So this is something you still have to manage yourself. But it's made a lot easier because we just need to update the Kafka custom resource to change this to whatever version we like. Broker replacement is also possible. So if we want to if we want to replace a broker because its underlying kubelet died for some reason, or maybe the persistent volume blew up, then all we need to do is delete the pod, and this will initiate a deployment of a new broker with the same name, which is important. So we have some consistency with the names of the brokers. So it will it's like a scaling operation. It will just deploy a whole new broker somewhere else, and if it needs to, it will create a new persistent volume claim, and the persistent volume claim will create a new persistent volume if that disk was destroyed somehow. And this process also allows us to move brokers if you want to do some kind of thing like preventive maintenance, and do it in a zero downtime way. We can use this deletion of pods to do that as well. I'm not going to get into too much detail about this because we have limited time, but basically the steps are listed here. Quickly go through them. We just find like the average byte rate or the maximum bit rate per partition, and this is used to control or throttle how fast partitions are moved off of the broker that we want to replace. So we don't saturate our network when this happens, because obviously a lot of data could be flowing over the network. So we use a partition reassignment tool. We give it a throttle. We move partitions off the broker we want to replace. We delete and replace that broker. And then we do the inverse of the partition assignment to move partitions back to the new broker that we just replaced, using that same throttle that we had discovered. We can also synchronize the cluster itself using Mirror Maker, which is bundled with an Apache Kafka release. So this is useful to set up disaster recovery or some kind of multi-data center requirement. So if you have an active passive cluster, which is just one cluster in one region that is having messages produced to it and maybe consumed from it too, and we want to synchronize those messages to another region where other consumers are consuming from as well, then we would set up active passive. If we have a requirement of setting having producers and consumers to our clusters across multiple regions, and then we have a much more complicated setup, which you can also enable with Mirror Maker, but that's kind of beyond the scope of this presentation. I just have a simple active passive cluster diagram described here. And what we would do in this case is one of the clusters needs to be Strimzi. They don't both have to be though. And we create this Kafka Mirror Maker custom resource. And the cluster operator watches this and then facilitates the running of Mirror Maker for us to synchronize between two arbitrary Kafka clusters. Monitoring is easy to do in Strimzi as well, and it's using the Prometheus stack to enable it. And this is done by using, Kafka brokers are Java applications, and they expose their metrics using Java's way of exposing metrics, its default way, JMX. So it just converts those metrics to Prometheus using the Prometheus JMX exporter project, and that just exposes a HTTP endpoint that can be scraped with all the metrics and their values. So Prometheus server will scrape it, and then the Prometheus server is kind of like a database of metrics, a time series database that we can perform queries on and do all sorts of interesting things with. We could maybe set up auto scaling if we wanted to, or we could just have our simple monitoring dashboard set up. And I have an example of a dashboard to show. So this is a simple dashboard we bundle with Lightbend Platform, so you can monitor your clusters. So this is a cluster that's running Lightbend pipelines, so it has some activity on it. It's just a simple 3-node cluster, and it has all of the metrics and all the bits of information we need to make sure that this cluster is healthy. So things like under-replicated partition counts, disk usage, which is Kafka's Achilles heel. We can't ever have our Kafka brokers run out of disk, or bad things would happen. We can set up alerts when we need to. Other JVM metrics, garbage collection metrics, bit rates, throughput metrics, and then more Kafka-specific metrics like request average, request handler metrics, and this is useful for determining if your broker is too busy or not. In this case, it's not busy at all, so this is in a good range right now. So in conclusion, we should ask the question, is running Kafka on Kubernetes safe? A lot of people caution against this. And like I said, the cluster resource managers like Mesos, Kubernetes, running stateful services was fairly difficult to do in the past and could be unreliable in some cases. But we're getting to a point where the concepts, especially in Kubernetes, are well understood, and the implementations are being used in production today and seem to be working out rather well. Nonetheless, Kelsey Hightower, a distributed systems software engineer from Google, cautions against using stateful workloads on Kubernetes if you don't really understand what's happening under the hood. And that's really good advice. And that leads me into this pros and cons list. On the pros side, there are a lot of companies running Kafka in production in this way, not necessarily using Strimzi, but for example, Confluent, the company behind Kafka, has an enterprise product called Confluent Cloud, and they're running this on Kubernetes clusters on Google Cloud and AWS using their own operator. It's a proprietary operator they use. And they run these clusters on behalf of clients all the time, and that seems to be working out very well for them. Also on the pros side is the Strimzi is backed by a commercial product and a full team of full-time software engineers at Red Hat that keep the quality level of the project very high. And finally, Kafka data, like if things do go wrong, I would argue that it would be the end of the world, because usually you use this for streaming data platforms, and that data is transient in nature. Obviously, we don't want to lose data, but maybe we have a little more flexibility when talking about Kafka data versus long-term storage data in something like HDFS or Cassandra in a more structured form. But nonetheless, persistent volume, stateful sets are relatively new concepts, and were beta for a long time in Kubernetes until somewhat recently. It's important to have experts on staff that understand Kubernetes really well, how the provisioners work under the hood, how they integrate with your cloud provider, for example, before you go into production. Because when things go wrong, you definitely need that knowledge in order to remedy the situation. There is also some drawbacks to using Strimzi. For example, the update strategy is rather simplistic. It's one at a time, at least as far as I know at this time. So it is more suited for smaller production clusters, like in the tens or very low hundreds, because it can take a while to do updates or do maintenance if you need to do it. But I would expect that in the future that will change and more complicated update strategies will become available. So here are the details of the Strimzi project. It's been stable for a while now, almost 6 months, more than 6 months now. 0.11.4 is the current version, and Lightbend Platform provides support for Strimzi in the last couple of releases. So before we wrap up, a couple of things I promised to go over. So Kafka Lag Exporter is a new open source project that I open sourced a couple of weeks ago. And this is to make it easy to monitor Kafka consumer group, lag, and latency of Apache Kafka apps. And its main features include integration with the Prometheus stack by exposing these metrics as Prometheus metrics. It also will estimate consumer group latency in time, which is pretty useful because that's how you often set up SLAs for your streaming platform. How far behind can you tolerate them to be? So having group latency in time versus just offsets is useful. And this diagram on the right-hand side is just from a blog post, which describes how that works. It supports Strimzi, so it does auto discovery of Strimzi clusters if you deploy it into Kubernetes, and it has a Helm chart too. So you can find more details about it with these links that we have here. Lightbend Platform is what Fast Data Platform has become, and it provides support for running pipelines, for building your data platforms on, as well as the reactive microservices, all the open source frameworks and toolkits that we provide support for. It runs on OpenShift, and there are plans to support other versions of Kubernetes or flavors of Kubernetes in the future. And we support Kafka using Strimzi on this platform. And here's a screenshot of the Lightbend pipelines console. So we just have a simple pipeline here. Each one of these things is a Streamlit, which is basically an Apache Spark or Akka Streams workload. And these connections are basically facilitated by Kafka. So everything's connecting to a Kafka topic in between each Streamlit. And then we do a lot of the heavy lifting for you in this product. So it's great for just getting started with building data pipelines, especially if you don't have a lot of expertise in this area. We make it super easy. So that's the presentation. Thank you very much for listening. This is just a shout out to a O'Reilly report that I co-authored with some colleagues called Designing Fast Data Application Architectures. Check it out. It's free on our website if you want to download it. Thanks.
All right. Thank you so much, Sean. Well, we are nearly out of time for the day, but we do have a few questions that I think would be good to answer. So one of our first questions, Sean, is can Strimzi be applied to a Kafka cluster already existing in Kubernetes?
Yeah, that's a good question. So yes and no. So it can't manage an already existing Kafka cluster. So the cluster operator can't manage something that already exists, but the topic operator can be used in a standalone way. So if you want to manage topic resources the same way Strimzi does, you can actually deploy that and point to that your pre-existing Kafka cluster. You just give it connection information to ZooKeeper and its brokers, and you can get that kind of functionality for free. But otherwise, no. Strimzi is a managed Kafka product or project, and it's meant to facilitate management of the Kafka cluster, and to do that, it needs control over the cluster itself. So sort of a yes and no answer to that question.
All right, thanks. Second question, in the various Strimzi storage modes, can brokers share the same persistent value, and can broker pods have separate individual persistent value / storage options?
Yeah, I assume you mean persistent volumes, and they can. So the first question was, do they support shared stores? So the answer there is no. It's using read-write once, which basically means that a persistent volume of read-write once can only mount one time to one pod. And we don't need, and that's fine because we don't care about sharing the volumes across brokers, because Kafka takes care of replication on our behalf at a higher level. That's part of what Kafka does. When you define topics, you can set an arbitrary number of replicas. So the replication happens at that level instead of at the persistent volume level. And I think the other part of the question was, can you have more than one persistent volume associated with a broker? And I did have a slide where I showed that. Yes, you can. You can have an arbitrary number of persistent volumes associated with one broker using their JBOD mode, just a bunch of disks. And that will help increase throughput to disk, because you kind of get like a sort of RAID-like behavior when you do that. And you can also increase the amount of storage per broker that way as well.
All right, thanks. Well, Sean, this was an excellent presentation. The feedback from the audience has been very positive. Thank you for joining us today and giving us a nice walkthrough of Strimzi and all of the related components. To our audience, thanks for joining us today as well. If you are a Lightbend customer and you have questions about using Strimzi with Kafka and Kubernetes as part of Lightbend pipelines and Lightbend Platform, just reach out to your Lightbend representative and we'll get you started. So thanks again, everybody. Have a wonderful day and see you next time.